So now that we know about damped mass spring systems, we actually know almost everything we can know about mass spring damper systems. See, mass spring damper. There's one more thing that's missing, and it's called the forcing function. The forcing function is essentially any functional expression that tells us an external force being applied onto the mass. Let's give this a force as a function of time. My apologies if that's not legible. Force as a function of time. And you could think of this as really anything. For example, if your friend is kind of just pushing it constantly, he's applying a constant 5 Newton force to the mass to the right, that counts as a forcing function. And not only does it count as a forcing function, you would also count it in the sum of the forces acting on the mass. So to give an example of a forcing function, let's draw a final example. Let's, instead of having our mass be on a frictionless surface, sideways, let's let it hang off of, I don't know, off of a non-moving wall, where it's subject to gravity. And let's just, for simplicity, let's just give it the spring. So no damper in this case, but if you wish as an exercise, you can extend it to have the damper. So let's give this a mass m, spring coefficient k, and also keep in mind, if we draw a force diagram, that the force of gravity is applied. And then, remember, we also have a force of the spring. Okay, right? We can use force diagrams to also construct our differential equations if necessary. But my apologies, this is an M. So let's take a look at our form one more time. The sum of all the forces acting on the block is going to be equal to the mass of the block times the acceleration it experiences. What's the forces acting on it in one way? Remember, if this is acting backwards, that's negative kx. So let's say negative kx plus mg is acting downwards. We'll call that the positive direction because it makes the spring get longer. So plus mg, well, that's quite the long m, mg is equal to mx double dot. So let's rearrange. We'll get, and let's also get rid of m simultaneously. So let's cross this out, divided by m. Now let's rearrange. We'll get x double dot plus omega naught squared. X is equal to g. We can solve this kind of equation using a different method. So I won't cover it, but I'll introduce it. Essentially, this is called a inhomogeneous or non-homogeneous constant coefficient linear differential equation. What the word non-homogeneous means is that this term right here is non-zero. That means it's inhomogeneous. That's a bad zero. I'll make it a little better. So if this term over here is anything that is not strictly zero at all times, in other words, the zero function, then it's inhomogeneous. And as we recall from this picture, this inhomogeneity is as a force constantly acting on the block. And it doesn't have to be a constant. We just chose it because gravity is a constant, and that's an easy intuitive example. We can choose it as any function of time. For example, it can be a sine, and you can have rockets on here that are thrusting according to a clock that's, operating sinusoidally, whatever you want. In this case, gravity is the simpler one. And to solve this kind of equation, we're going to have a general solution, which is going to be the superposition of the homogeneous solution. In other words, take this equation where the g is not there, where it's just zero, solve it. That's your homogeneous. And then to it, add a particular solution. Now, your particular solution is going to be of the form of your forcing function. Why? Because what you want to do is you want to plug in your particular solution, and given up to constants, you want to be able to take the derivatives as necessary, and it's going to look like your forcing function. Why? If I have, x double prime plus x is equal to e to the x, there's no way I'm finding a solution. That's a bad, sorry. not e to the x, e to the t, there we go. There's no way I'm finding a solution to this that doesn't look like e to the t. Because if it's a polynomial, for example, the second derivative of a polynomial is a polynomial, plus a polynomial is still a polynomial. A polynomial is never going to equal an exponential, right? In most cases. For our case, it's never going to be an exponential. So instead, we say that the forcing function determines the form of our particular solution. And I say form very literally. It's going to look the same. So broadly speaking, we have three forms. We have forms of e to the t, as well as the forms of a sinusoid and of a polynomial. So in this case, we don't just make our particular solution a guess specifically of e to the t or sine or x to the n. What we'd want to do is make a guess of a constant coefficient multiple of these terms. So for example, if we have our differential equation is equal to e to the 5t, we're going to guess that our solution is of the form a e to the 5t, right? And generally, one of the first steps, or the first step in solving for a inhomogeneous solution is solving the homogeneous case. Why? Because if you find that c1 e to the 5t, for this case, is already a solution, what you have to do is you have to add a factor of x in front of it. And if there's already a solution, factor of x, you add x squared and so on. That's the case for e. As we mentioned, for sines, whenever you have a sine, you also have the possibility of developing a cosine through a derivative. So you make guesses of the form a sine of whatever your term is, let's say alpha t, plus b cosine of, again, your same term, alpha t. And the same principle applies if there's already a solution in the form sine alpha t plus cosine alpha t, just add an x in front of it and make sure you get both of them. And for the case of the polynomial form in homogeneity, what we have to guess is also a polynomial form, but again, we don't just guess x to the n. Just like for the sinusoidal case or the cosinusoidal case, we had to account for the derivatives, we also have to account for the derivatives of the polynomial. So if we have an equation, for example, x double dot plus x, it doesn't have to be dot in this case, but whatever, is equal to t cubed, our guess is going to include t cubed, and in fact it has to include t cubed because otherwise we can't get a t cubed here. But it's also going to have to include, that's a b, it's also going to have to include a t squared, a t, and a t to the 0, or just a 1 times a coefficient. And again, the reason is because we have differentiation occurring, so we need to make sure that there's opportunity for all these coefficients to cancel out. So right over here, you can see a reference of particular inhomogeneities. So this would be of the form something equals g of x. Particular non-homogeneities are forcing functions, and examples of what you would guess. So for a constant, you guess a constant multiple. For a polynomial, you guess a polynomial, same thing. For a sine or a cosine, you guess both. For an exponential, you guess an exponential. And when you begin to combine terms, for example, by multiplication, the form of your guess is the same. You combine terms. Again, with this example number 9, recall that we have to include all the derivatives of the polynomial, of course, except 0. And in the case where we combine all of them, you can see it does get a little big, but it's intimidating, not difficult. So you can try some of these as an exercise if you like. And as we've shown in previous, we might not have shown, but we know that the superposition of solutions is also a solution. So for example, if we have e to the x plus sine 4x as our non-homogeneity, then if we guess a solution a e to the 5x plus b cosine 4x plus c sine 4x, that's going to be a valid particular solution. So we can take superpositions of forcing functions and products of forcing functions, and we can form appropriate guesses. So once we have our homogeneous solution by setting g equals 0, and we've made our particular solution guess, keeping in mind that we don't repeat any solutions in y of h, right? So, for example, if we have a e to the 5x, but our homogeneous solution already has an e to the 5x, then we just add an x to it. If our homogeneous solution has two 5s in its roots, and we have an e to the 5x and x e to the 5x, then we add another x here. So this becomes ax squared e to the 5x, and so on. We have our homogeneous solution, we have a particular solution, so their sum is going to be the general solution, and that's the end of the problem. So in this case, with the spring, I'm not going to solve it. You can do so as an exercise. What we're going to have is we're going to have a homogeneous solution that looks like, in fact, we've already solved the left side of this equation, the homogeneous case where g is 0. We know that this part, when g is equal to 0, or when the right side is equal to 0, is just going to be a sine plus a cosine, a scaled form, where the characteristic frequency is omega naught. And then if we think about this and we go reference our chart, well, g is just a constant, 9.81. So if we look any constant, we're going to guess a particular solution is just another constant. So if we guess that it's just another constant, what we're going to get is we're going to get some constant sine plus another constant cosine, and we don't worry about the actual numbers, plus a third constant. So all this is a sinusoidal wave that's shifted up or down depending on the constant. And in this case, it's not necessarily true that C3 is equal to G. If you can plug it in and check as an exercise. And by plug it in, I mean plug in the guess solution and solve for the system of equations that comes out of this. And see what C3 is in this case, because you should have a value for C3, not necessarily C1 and C2 without initial values. So that's it. I hope it helps. This has been a brief introduction to mass spring damper systems along with forcing functions and undetermined coefficients.